that is what I'm going to say on big O notation. Was that okay? A little bit you knew from 1019, a little bit you get from Jeff's wisdom. All right? All right, so now I think I told you a little bit about summing already, right? What I think is dumb in 1019 is that they teach you big O notation, and then they teach you sums and make you get the constant right, right? The whole point was we don't care about the constants, all right? So when I first started making these notes and it turned into a book for 3101, I was all thinking about what's the best way to teach students how to do addition, all right? So, you know, in this example, 1 plus 2 up to n, well, you might have even done this in high school, right? So you see here we have 2 copies of it, and you put the 2 copies together, and you see how many we have, and you divide by 2, and you get the answer, right? And the story goes is that Gauss was acting out in class. Why? Because he's bored. And his teacher says, add up the numbers between 1 and 100, and he does it in 10 minutes. And was his teacher happy? Probably not, right? So, right. All right, so we're going to be looking at sums like this. And what I want to focus on is the middle term compared to the last term, right? I want to know how fast are the things I'm adding growing, right? And here they're growing linearly, right? And if you look at the middle guy, the middle is n over 2, right? What is f of n over 2? In this case, it's n over 2, right? N over 2, it's within a constant of n. If I don't care about constants, then the middle term is the same as the last term, right? N over 2 and n, they're the same. Now, how many terms are there? Well, they're n terms, but some of them are small. How many are them after the middle? They're n over 2 after the middle, right? So should we call it n terms, or should we call it n over 2 terms? Does it matter? No, because the constant over 2 doesn't matter, right? So in this case, we can just simply say that the sum is the number of terms times the last term and go home, right? Because the number of terms is n, the last term is n times n is n squared. We're done, right? Right? And it's true whenever they're growing slowly. And maybe I don't give you other examples, all right? But in grade 9, my math teacher told me not to come to class anymore, and she gave me problems. And one of her problems was to sum up 1 squared plus 2 squared plus 3 squared, right? And that took me a while. But then you can say, well, if we don't care about the constant in front, well, what's the middle term? It's n over 2 squared, right? What's n over 2 squared? Well, it's n squared over 4, right? So the middle term is big O of the last term. So what's the number of terms? N. What's the last term? N squared. What's the sum? Order n cubed, right? It's very useful. In fact, this could be sum of f of I for any polynomial, right? Any polynomial. And it just is, you take the big O of the last term multiplied by the number of terms and you're done. All right? Easy. Everybody get that? All right, now, this isn't as good. They're growing fast. Am I giving you any pictures here? Yeah, here's a picture. All right? So every term is twice the previous term. And if you look at, proof by picture, what's the sum of the terms up to 64? It's double 64 minus 1, right? And we could go through a whole proof of that, right? But if you don't care about that, right, the key is it's dominated. Let's see. Here, that's what it goes up to, what is there, right? We could do some crazy math, which I'm trying to argue we don't need to do, right? And what is it dominated by? It's dominated by the biggest term, right? Now, you see that's kind of a bit of a lie here, right? We got the -1 doesn't really matter. What is the biggest term is n to the r. Well, this is r times bigger, but we're dividing by an r -1, and we don't care about constants anyway, right? So everybody good? It's dominated by, right? Now, so that's the big picture. It's dominated by the biggest term. Now, here's a little question. Why am I saying the biggest term and not saying the last term? It might not be the biggest, right? In fact, in this equation here, what might be the biggest? The first one, right? When r is less than 1, right? Then they're shrinking, right? So so this is true whenever it's sort of growing fast. And here, right? What's the sum of 1 plus a half plus a quarter, right? It sums up to pretty much 2, right? And that's where the biggest term is the first one. So it's big O of the first term. And why is this also kind of interesting? Suppose your first term is something weird, and your last term is something weird, and you know that it's going up by at least the factor of 2, right? Then, or it's going down by a factor of 2, right? You don't even know. It's just changing by it, right? Then you know it's going to be dominated by this one or this one, right? And what's the answer? Whichever one's bigger, right? Whichever one's bigger. All right. Right. So everybody gets in this case, the first term's a constant, but the first term might not be a constant. All right. All right. People know this sum. Did you do this, guys? It's called the harmonic sum. Comes from sound, harmonics. And anybody know what it adds up to? Adds up to, it adds up to, let's see, here, let's do a proof by picture, right? Just so that people can visualize a little bit more, right? This is the sum of 1, right? It's kind of like the integral under the curve, right? The sum of 1 is n, right? Everybody see that? Because how many terms we have? We have n terms, and the biggest term is 1, right? So now we're summing square root. What does it come up to? Now we're summing something. Now this guy is shrinking, so this adds up to 2, right? And now this is bigger than that, right? 1 over I is bigger than this exponential, right? So what does it go to? And if you've taken calculus, you might know the integral of 1 over I. And it boils down to log n, right? And here's kind of a proof using a discrete mode of proof. We look at the first term and the first 2 and the first 4 and the first 8, right? We group them. And then you can argue that all of these terms, all these groups add up to something between 1 and a half, right? And how many groups do we have, right? We have log groups. Everybody kind of get that? Right, so if we were to only add up to here, then the answer would be, well, we got 4 groups, and each group is between 1/2 and 1, right? If you go to n, then they're log n groups, right? And if you want to be more precise, the sum is ln, right? It's base, you do it base e. All right, so there's that one, that harmonic sum. It's the same as integrating, right? People sort of see it's the same as integrating. And that's all I got to say about sums. Everybody good about that? This just says, right, if you're growing fast, then it's dominated by the sum is dominated by the biggest guy, right? If you're shrinking fast, here you're shrinking fast, it's dominated by the first term, right? If you're here at log, then you're here at 1 over n, then you got your harmonics. And if you're here at some sort of thing, then polynomial, then it's the number of terms times the last term, right? So that'll help you do quick sums. And here's a little chart and some examples. Should we do some examples? Are you kind of good? All right, I mean, here we say, D is say D is 5. How do I sum up 1 to the 5, 2 to the 5, 3 to the 5, right? Well, it's going to be order n to the 6, right? Same as if you were integrated, right? If you're like, this guy here is double exponential, right? Well, it's so dominated by the biggest term, right? And here guys are shrinking. So everybody good? So people ask what's going to be on the test. You know, we'll probably be 3 multiple choice questions on this. You know? Yeah, that's just saying the same thing. All right, everybody go to that? Here's some log properties you should know, right? A to the b plus c is a to the b. When you're multiplying, you add the exponents. Right? Do people know that? If you don't know it, you should know it. A to the b to the c. Well, I got a to the b, and then a to the b, and a to the b, a to the b. How many a's do I have? Well, I got b of them, and then b of them, and b of them. I got c groups of b, right? So I got b times c of them, right? Should we do any more of these, or you kind of? Anyway, you should know these if you're in computer science. All right, so we're doing the logic now, a game. Right? Have I done with? Do this game so often with people. Have I played this game with you? It's a good game, right? So, right? And so how is, we just did this a minute ago. Why is it an important game? Is because when I want to prove that something is computable, I come up with a Java program, and then my adversary comes up with an input, right? And we don't want to bound how big the Java program can be. It could be big, 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 right? But then your adversary is going to give you a bigger input. Like in the game, you can say 1 trillion, and I'll say 1,000,001,000, right? You give me a Java program that's 1 trillion characters long, I'm going to give you an input that's bigger, right? So you can't brute force it. Right? In fact, if you want to go back to think about machine learning, right? How many parameters they have. If you have more parameters than there is data, then they can just memorize the data, right? And that's called overfitting. And the problem with that is then it might not generalize well to data that if they've just memorized the answers and they haven't understood it, then it doesn't generalize well. That's sort of off topic. All right, so here's the game, right? The game is saying for every x, adversary, how do you play the game? How do I prove for all x? Let x be arbitrary, right? Here, give me an arbitrary x. Let me tell you something about the word arbitrary x, that people get confused, right? Sometimes what I might mean about that is give me a typical x, right? What does that mean? It might mean give me a nice x. It might give me a random x, right? No, this is, in the game, give me a worst case x given to me by my adversary, right? All right, so my adversary gives me a bad x. Now, an advantage of this game is that whoever goes second has a huge advantage, right? Why is it an advantage? I got to come up with a y, but I know your x, and I'm going to make my my y bigger, right? And that's the game, right? So in this, right here, we've got various examples. Oh, here this is kind of funny anyway, right? So all of these, every person loves some politician, right? Right? But what's the difference is in this one, they're all loving the same politician, right? In this one, this was made an earlier election, right? In this one, they could be different politicians, right? And so here we're saying, how would we say in English? We could say there is a politician, right? There's one politician that works for every person, right? Here we're kind of saying for each voter, there's a politician, right? We try to say that in English. Everybody kind of see that? Now, let me tell you why English is bad, right? What's the multiplicative inverse of 3 is a third, right? And we're not talking about 0 here, right? Because that's bad. But there is a multiplicative inverse for every real other than 0, right? Now, but you see it's the same sentence structure. You note the sentence structure? And clearly different reals have different inverses, right? So you're not going to get it from English. Now down here is a sentence. It's the same structure, right? For each person, there is God, right? Now if you're a Hindu, they might be different gods. But if you're a good God-fearing Christian, we all have the same God, right? So I'm just saying it's confusing. And so you want to be clear. And this says, you got to tell me the politician. There exists one politician that works for every voter, right? Well, this says, you tell me your voter, and I'll find you a politician, right? I can come up with the politician afterwards. You say Sam, I'll say Scheer. You say John, I'll say Trudeau, right? It's a different game. Everybody see that? And so this one is a statement about politicians, right? It says there is a politician that has the property that he's loved by everybody or she's loved by everybody. Well, this one down here is a statement about voters, right? It says every voter has the property that they love somebody, right? Which probably isn't true, right? I'm sure there are people out there who don't love anybody. Are people following this? And let me pause for a minute if I haven't told you the story. I have a little brother who's as big as me, but he's much younger than me. And he was doing his PhD in mathematics at U of T. Did I tell you this? He was taking a course in set theory, which I'd never taken. It's hard stuff. And he comes to me with his homework. And I say, let's write it down. What do we know in the first logic statement? Let's write down what we're trying to prove. Let's play it like a game. And it was just obvious. The answer just fell out and it was obvious. All right? It's all about knowing how to play the game. All right, so this is the one we've done already, right? We're saying computational problem P, what does it do? For every input, we know what the required output is, right? So the problem, sorting, says you give me a bunch of numbers and the output is them sorted, right? What is an algorithm? It's a machine, like insertion sort is an algorithm, right? You give me right? You give me a machine and you give me an input and I can run the machine on the input, right? And what do I need to know about the machine? It has a finite description, right? That's all we know about it. And it might run forever, right? And then we can say P is computable, right? Well, if there's a single algorithm that computes it, right? There exists one machine that for every input gets you the right answer, right? And right, so you want to understand this better. What I recommend, let's see, we're going to kind of say here, right? In some ways, P is the free variable, right? So it's a statement about P. What is it saying about P? It's saying P is computable, I think. And then it says something about the existence of this machine. All right, so anyway, here we go. Computes, right? What does compute mean? Turing machine M computes problem P, right? And then what are we saying? Well, there exists a machine that computes it, right? And how do you write that? Well, you write it for every input. The machine gives you the right answer, right? And then you say there is a machine that works for every input, right? And so I know this isn't really part of the course, but I really do think if I push it to everybody who's willing to listen, it will help you in many courses. All right? Right, so here it's just playing the game again, right? We have the two players. We read the statement from left to right. The first guy, if it's a prover, sees exists M. He exists, he has to come up with the machine, right? And then when it's for all, the adversary comes up with it, right? And the statement's true if the prover can always win, right? And the order you play matters, right? So how would we do this if we were in the, here's this course right now. Can I solve problem P? I claim yes. Why? Because I got a machine that can solve it. Okay. Oh, yeah? Does it work on this input? Yeah, it works on this input. Right? Right? So now, have you taken 2001 yet? Right? So you have to prove that the halting problem is not decidable. Right? So you have to be able to write that down. You have to take the negation. Right? You bring the negation in and you swap the exist and the for alls. So how do you do it? You say, you give me a machine, I'll give you an input that doesn't solve the halting problem, right? Halting problem is not computable. Why? You give me any Turing machine, I'll find an input in which it gives the wrong answer, right? And we do it this weird diagonalization proof, right? Right? I have a machine that claims to work, right? For all M, then I find an input for what it doesn't work. Right? Everybody see the game? All right, so here's the fun. We did this already, right? So look at the halting problem is undecidable. Is it true that for every input, there's a machine that gives you the right answer? Look at that. For every input, there's a machine that gives you the right answer. How many people think it's true? How many people think it's false? How many people have no idea? You're right. All right? Okay, let's play the game. All right? Right? The order matters. This is M followed by I. This is I followed by M. Remember I told you I would beat you if you did this in the wrong order, right? So just play the game, all right? I'm going to prove to you that the statement's true, right? You give me some input, right? Now, what do I do with it? Well, I don't know whether the halting problem says yes or no on this input, right? Because I can't solve the halting problem. But I know the halting problem says it's yes or it says no, right? I don't know which. All right, so now my job is to come up with a machine. All right, now this is where it's subtle, right? Let's create two machines, right? One machine, what it does is for any input says yes. For the other machine, for any input, it says no. All right? Now, one of these machines gives the right answer for our input. Do I know which? No. Do I know that one of them works? Yes. One of these works, right? For every input, there exists a machine that happens to give the right answer. Because there are only two answers, right? So I only need two machines, right? Does that make sense? It's just, I'm telling you, be careful with these logic things, all right? Right, so here we can say some other things, right? Here I want to say computational problem P is computable in poly time. Why? There exists a machine that, for all inputs, gives the right answer, right? Here I'm saying it gives the right answer, right? There exists a machine that, for all inputs, gives the right answer. And what about the running time? There exists a machine, I give you a machine, and I give you the C, right? Here's the C, and the running time will be bounded by n to the C, right? Kind of see that? Right? If I tell you I can sort in n squared time, what am I giving you? I'm giving you the sorting algorithm, and I'm giving you the 2, right? I give you the sorting algorithm, and I give you the 2, and then you give me an input, and I win if my program gives the right answer and doesn't run in more than n squared time, right? So not computable, right? You just have to take the negation of it, right? And even me, I don't know, I've been doing this a long time. If you were to get me to write down, how do you say it's not in poly time, I would have a hard time doing it, right? But if I write down this one, I just take the negation of it using logic, right? How do you take the exist turns into for alls, and the ands turn into ors, and right? Exponential time, right? Same deal, right? And what does this say? This says there is a problem that can't be solved in polynomial time, but can be solved in exponential time, right? And that's it for running time. Everybody good with running time? How much time do we got left? 14 minutes. It's amazing how much time there's always left. I really go too fast. Are people following this more or less? You guys good? All right, 14 minutes. Do ask questions though, right? So the next topic is recursion. Yes. What is what? Good question. All right. Let me tell you a little bit. Let's say I give you a Boolean circuit with n inputs, right? And I ask, if I give you the assignment, how long does it take to know what the output is? That's fast, right? How long does it take to find an assignment? Well, they're 2 to the n assignments, and it takes me 2 to the n to check them all. All right? Now, instead, let me give you a multivariate polynomial, right? So these variables are integers. It's an integer, right? So the polynomial might be x cubed times y squared plus, right? Some multivariate polynomial, right? If I give you an assignment of the variables, you can check it fast, right? But how long does it take to find a solution, right? You got to check all solutions. How many solutions are there? Well, there are an infinite number of integers, right? So that's an undecidable problem given a polynomial, multivariate polynomial. Is it satisfiable, right? Can you make it 0? You think, come on, that's easy, right? It took 20, 30, 40 years after Turing to prove that one, because that one's harder, right? But the halting problem is kind of like that. Suppose I give you a machine, an input, and a running time. And I want, does this machine on this input halt in this amount of time, right? Can I solve that problem? Yeah, you just run it and see if it stops, right? Because you're guaranteed. What do we need for an algorithm? We're guaranteed that on every input, you stop and give the right answer, right? So if you say, does this machine on this input halt in 1 billion steps, I run it for 1 billion steps, and I halt, and I get the right answer, right? But now, I don't want to tell you the billion. It's kind of like, well, we need to learn the running time. If we knew the running time, we could solve the problem, right? But we don't know the running time. So you have to search for all running times. And there are an infinite number of them, right? So how would you solve the halting problem? Well, you would run the machine. And if it halts, you say, great, it halts. But if it runs for 1 million years, what do you say then? No, you don't know. It could halt tomorrow, right? And that's, yeah, in fact, there were models of computation before Turing that can really compute anything that you would ever want to compute. I'm going to say recursive, these recursive programs come up by Gödel, but no, automata is up to Turing. Turing does automata, right? The difference between Gödel's machines and Turing's machines is Gödel's machines always halted, and Turing machines might run forever. And the ability to run longer gives you more computational power, right? But then it gives you problems that you can't solve because you don't know whether they'll stop. Did that answer your question? All right. Now we're really running out of time. We got 9 minutes. Anything anybody wants to talk about for 9 minutes? Should we go home? Should we bring up slides? You want to go home? All right. Talk to me if you need to. Let's go home. Have a good weekend. Next class, we'll finish up recursion, balance trees, hash tables, graphs. You know, quite frankly, let me tell you my concern. Sometimes my concern is that we're falling behind. Now my concern is we're whipping through this course, right? There's a good chance we run out of material. What will we do then? Start at the beginning and do it again. I don't know. All right, everybody good?
Hey,
So
Professor.
really ask more questions.
Hello, Professor.
We're running out of slides. Have a good weekend.
Hello, Professor.
Have a good weekend.
I guess I can't be heard. Hey, Jackie, what's up?
What's up? What's up?
What's up, man?
What's going on? Hello?
Hello.
Oh. Oh, it's working. No
It
way.
is. Nice.
You can end for all.
I guess you couldn't hear me, Smash.
Nah, it was probably muted on his end.
Smash. I
Unlucky.
wanted the big old talker.
No,
Remember?
hey
Yeah.
God.
Yeah, unfortunate. Remember, you're still recording, by the way, the lecture.
Oh,
Yeah, so let's get out of here so the recording
okay.
ends.